Okay, now we're going to consider qubits, higher dimensions, and the inner product. Okay, the quantum state, let's write that down again. Psi is equal to alpha 0 plus beta 1. Okay, so this is possibly the simplest quantum state we can consider. It's a two-dimensional quantum state. Now, this sort of state is also known as a quantum bit or a qubit. So we call such a state a qubit. So a two-level system has two bases here, is known as a qubit. This is like the quantum version of a bit. Classically, we have say 0 and 1. We often deal with that in basically our everyday life. But here we have the quantum version of that, which now it's now a vector 0 and a vector ket 1. So we still have the analogies between the 0 and 1 as we have in the classical world, and then by classical I just mean our everyday world that we're used to. But you see the difference now is that we have a superposition of both of them. Now superposition just simply means an addition of a certain amount of things. In this case we have two things. So we can have both of them at the same time. Now ket psi, so this is our ket psi, might represent the superposition of two spin states of an electron. So in that instance we can write it as ket psi alpha spin up plus beta spin down. Or alternatively, a photon in a superposition of two different polarizations. Okay, so we can write ket psi is equal to alpha ket h plus beta ket v, where this now stands for the horizontal polarization and the vertical polarizations. Okay, so these corresponds to polarizations. And this is spins of an electron. Okay, so we can extend this qubit here. We have here. At the moment, it's a two-level system. We can actually extend it to much higher dimensions. So, for example, let's scroll down a little bit. There we go. Now we can actually write psi, ket psi, is equal to alpha naught 0 plus alpha 1 plus alpha 2 and we can keep going and we can add that onto all the way up to alpha n minus 1 n minus 1. So before we just had two-level systems, now we can go up to n minus 1 systems. Well, we can actually write this in a more simplified version here. So we can say it's equal to I is equal to 0, from I is equal to 0 up to n minus 1, which we know we've done here. The amplitudes we can write alpha I, and the bases now ket I. So you can see we go up to, if we expand this out, we get this. Now this whole thing here is an n-dimensional quantum state. If we want to write this in terms of the matrix representations, which we did before with the two-level system qubit, then we can write it as alpha naught, alpha 1, dot dot dot, all the way down to alpha n minus 1. So remember, the ket can be written as a column vector, and we have the coefficients here, starting from the beginning all the way down to the last one. Note that when two vectors are orthogonal, physically it means that the corresponding physical states which the kets represent can be fully distinguishable. So let's go back here, scroll up a little bit and see what I mean by that. So before we talked about electron spins and polarizations. So we said physically corresponds to physical states which the kets represent can be fully distinguishable. So we know basis, if it forms a basis, and each one of those bases are distinguishable. And that's also true when we have the physical representation here. So here ket horizontal is always distinguishable from the vertical, and spin up is always distinguishable from the spin down. An important quantity in relation to two quantum states, let's say in this case, let's say we've got psi and phi. So an important quantity when we have these two is the inner product. So remember we wrote the inner product as phi psi. And this sort of calculation comes along in a lot of places in quantum information. One that comes to mind, for instance, might be cloning or distinguishability. And we have to work out these sorts of mathematical relations. So let's do an example of that. Now let's suppose we define, as we did before, we'll use the same sort of definition of psi. So psi summing up over I, all the coefficients I and ket I, and let's define phi in a similar sort of way, again summing over different complex amplitude. Let's call this beta, j, and j here. Okay, so now what we want to do is find the inner product. Okay, so the inner product, let's calculate that now. Now if we look at what we want here, we want to calculate this quantity here. Well, remember we have the ket here, so we've got that defined, that's fine. And now we want the bra of this. So remember the bra is written like this. It's kind of like a backwards version, if you like, of the ket. Now we're still going to sum over all the j's. Here we put again the backward version, the bra of j, and remember all of these become complex now. Okay, they're all complex numbers. We have the complex conjugate, sorry, of this variable. Okay, so let's start working this out now. So we've got the inner product of these two vectors is equal to, let's just write them out explicitly first. So just writing them down what we had over here, j, this should be here j, so that's j. So this is all multiplied by this guy here. So this is summation I, alpha I. Now remember what we said before. Whenever we have coefficients such as alpha I and beta j conjugate, they don't take part at all in anything to do with these kets. Okay, so these kets will act on themselves, and these guys here will get taken out the front along with the summation sign. Okay, so with that in mind, let's bring out the summations. So we have two summations here, I and j. Okay, we've got beta j conjugate. Let's bring the other guy out, alpha I. Now these j and i's, kets and bras, only act on themselves, only concerned about themselves here. So these guys come out. Okay, so what do we do next? Well, remember we talked about orthogonal bases. So there's only two possibilities for this. This can either be this can either be a 0, or this can either be a 1. Okay, when it's 0 when I does not equal j. Remember, if this was 0 and 1, two different things. If j was 0, I is 1. This whole thing is orthogonal, so it's 0. Okay. When this inner product here is equal to 1, it only happens when I is equal to j. So our next step then is recognizing this fact is to break them up into these different cases. So let's assume that I is equal to j. Okay. So what that means, wherever we see j, we put I. So we see a j there, put I. I stays the same here. And then we have I here and I there. So this is this case here. Okay. Now we don't have everything yet. We also need to add the other case. So when I, the leftover components, when I does not equal j. Okay, so so now we put beta here, I, let's keep that as j from before, star, and alpha I. Okay, now this is I, j again. Okay, but the difference from up here is we've selected out the times when this does not, I does not equal j. Now, what happens in these times here? We can actually get rid of this completely because when I does not equal j, we can remove that. So let's get rid of this whole term here. This goes to 0. We know from what we discussed in the last lecture, when these two are the same, this is equal to 1. Okay? So what that means now is we can actually write it's equal to summation I, beta I, star, alpha I. Okay? So that's the inner product. So what is this? This is equal to, this is what we've just worked out, the inner product between these two kets, these two quantum states.